Welcome to the 19th lecture in the course of Industrial Engineering and Operations Research. We are discussing scheduling. Scheduling part 1 is complete. There we told many heuristic methods to schedule the job. Suppose you have got only one machine, but there are 4 or 5 jobs waiting. So, in what sequence you should do the job, which job should be done first, then which job should be done second, which job should be done third, like that. So, there are many heuristic methods, and we found that method of the shortest processing time was very good. That means among the remaining job, whichever takes less time, that should be done like that. So, shortest processing time first, but if you know due date is of concern, that if you know customer cannot afford any lateness in the job, any tardiness in the job, in that case you should do that, honor the due date, whichever due date is there, that should be done. Or in case that suppose it is some public type of agency and customers are very cautious, they say that okay, we came first, we have to be served first, then you have to follow simple first come first served rule. Okay. So, many different situations are there, in that one has to take decision, but mathematical techniques do guide us. So, I am now going to discuss one more thing, that you know that one performance measure, that is called critical ratio. For organizations and industries that have due dates, the critical ratio for sequencing jobs is beneficial. So, critical ratio, that is denoted by CR, is an index number computed by dividing the time remaining until due date by the work time remaining. So, that means suppose the due date was say April 10, okay. Suppose 10/4/25 was the due date. Now, I am on the 6th April, 6th April you have to take decision. So, it is only 4 days remaining, 4 days remaining, okay. But then your suppose work requires still 8 days time, okay. Suppose 8 days more time is needed, 8 days processing is needed. That means already you might have processing needed, but you have 8 days. So, it is so therefore, what you do, that you see that 4 divided by 8. So, your critical ratio in this case has come time remaining until due date. So, time is only 4 days is remaining, but the work time is remaining 8 days. That means critical ratio is 0.5. Okay. So, critical ratio is 0.5, and critical ratio performs better than first come first served method, SPT, EDD, first come first served, FCFS. SPT means shortest processing time, EDD means earliest due date, LPT means longest processing time on the average job readiness criteria. So, what happens if we pay attention to CRR, then our job readiness can be reduced. So, from job readiness point of view, among FCFS, SPT, EDD, LPT and CR is better. So, critical ratio gives priority to jobs that must be done to keep shipping on the schedule. So, a job with a low critical ratio, that is less than 1, is one that is falling behind schedule. See, here we got 4/8, that means 0.5. So, it is less than 1, that means this job is falling behind the schedule. Why it is falling behind the schedule? Because 4 days are only remaining. I am already on 6th April evening, and I am seeing that by 10th evening I have to give the job. So, 7, 8, 9, 10 only 4 days are remaining, but it requires 8 days work, because job requires many things. Now, it can be completed only in 8 days. So, therefore, 4/8, that means 0.5, it is less than 1. So, therefore, it is naturally falling behind schedule. So, if CR is exactly 1, then the job is on schedule. Suppose only 4 days were left, and work was also remaining of 4 days, then 4 by 4 would have been 1, then it is okay. So CR greater than 1 means the job is ahead of schedule and has some slack. Slack means some looseness. You can afford to be little bit relaxed. Okay. Suppose on 6th April you would have seen and you would have thought that, oh, okay, finally say one heat treatment is needed and that will require 24 days and 1 day only. So you can say that, okay, 4 by 1 and it would have come 4, then you would have said yes, okay, critical ratio is more than 1, so I have slackness. So CR is equal to time remaining, okay, and work divided by work days remaining. That means how much more work day has to be done. So that is time remaining. How you will find out? You see the due date minus today's date. Like due date was 10th April, so you say due date is 10 and today's date was 6. So 10 minus 6 is equal to 4, like that. And work lead time remaining, that means work time remaining, that means it is also called lead time, that how much time is needed. So let us see the example. Suppose today is day 2 for an industry's production schedule. 3 jobs on order as shown in table. Then job A due date is 13, here work days is 10 and this is 5, this is 4, 9 and work days remaining is 7. So compute the critical ratio for each one of them. Suppose this is 13, due date is 13 but today is 2. So that means 11 days remaining, time remaining divided by 10. So it comes out to be 1.1 and second is 5 minus 2 because 5 days are remaining and then today's date is day is 2. Okay, so 5 minus 2 and divided by 4 because 4 days work is remaining. So you have to say 4 and this becomes 0.75. So critical ratio becomes 0.75 and priority order is, now this we discuss priority order later on. I just let us calculate the critical ratio. So 9 minus 2, due date is 9, today is 2. So work remaining 7 but it takes 7 days work. So 7 by 7 is 1. So you see that it is critical ratio is 1 here, it is 0.75 here, it is 1.1. So B is basically having critical ratio of 0.75. That means B is basically behind the schedule. Okay, that means it is very critical, 0.75. A has got some slackness, okay, because okay we can be relaxed, and C has got is exactly on schedule. Okay. So job B has a critical ratio of less than 1, that is 0.75, meaning it will be late unless expedited. So you be alert, do something, otherwise it will be late. Do something means employ the another machine, hire another worker, whatever way, otherwise normally it will take that much time. Thus therefore right now you have to give more priority to B. So therefore its critical ratio is less. So therefore it should be done first. So its priority order has become 1. And job C is on time. So you just give it 2. And job A has some slack. This is 1.1. Once job B is completed, the critical ratios for job A and C to determine whether their priority change or not, that also you can do. But right now this is B has to be done first, followed by C and followed by C. So this is first, this is second and this will be third in order. So that is how that we can make use of the critical ratio. So in scheduling system, the critical ratio rule can help in the following ways: determine the status of a specific job, that how much time is remaining, how much more work has to be done; establish relative priority among jobs on a common basis; then adjust the priorities. So establish relative priorities, we have done that, we have done priority here 1, 2, 3, and establish relative priorities among jobs on a common basis, and adjust priorities and revise schedules automatically for changes in both demand and job progress, and dynamically track job progress. So this has to be done dynamically, because maybe today you are seeing that work days remaining 7, but maybe tomorrow the situation may be different, because somebody might have noted that okay, 7 days work is there, now let me do fast, and then he does fast, and then naturally that it becomes reduces, Or sometimes what happens that although the work is remaining for 7 days, but today due to heavy rainfall somebody could not come and could not join the duty, and therefore the job further got delayed. So that type of situation may also be there. So you always dynamically track job progress. So be in that one. Now let me, so after that I am now taking up one simple problem that is called sequencing problem, that you know that suppose you have to do that jobs, okay, on only one machine. So we say that problem of preparing optimum timetable to support the production schedule. The most common objective is minimization of the total elapsed time. So suppose n jobs are to be processed one at a time on each of m machines. There are m machines actually available. So and there are n jobs, and order of machines is known, and the number of possible sequences can be factorial n into m. How that? Because on one machine I can assign that, say, some sequence. Suppose there are, we can understand with the example, suppose there are 10 jobs to be processed on 4 machines. Okay. On one machine there are factorial 10 ways to assign the job. So we have done that in this sequence. We can do that in this machine 10th job can be done first, then 9th can be done this one, then 8th. So there are total these many factorial 10 comes out to be 36,28,800. that means 3 million, and then this is a 3.6 million type of thing it comes. Okay. So this is this one. Okay. So 1, 2, 3, 4, 5, 6, 7. So you see 36 lakh. Okay. 28,800 wage are there, but there are 4 machines, hence total wage how many? That is multiply by this wage and this way into this way into this way. So that means 1.734 into 10 to the power 26. Obviously huge number of wage are there, so we cannot do it in this way. So we have to find out that proper way to do that. So Johnson has given some rule, and this rule he has given sequencing n jobs on 2 machines. Okay. That is Johnson's rule. So and machines are there. It is slightly different from scheduling problem, where I used to do one job at a time, what we explained. But here what happens, there are 2 machines. Okay. Say machine M, M1, and then machine M2, and let us say jobs are done in a sequence, that first M1 will be done, then the same job will go to M2 machine, and when this job is being machined at M2, then another machine is also machining something. Okay. So Johnson said that it minimizes the total time for sequencing a group of jobs through 2 work centers while minimizing total idle time in the work center. This is the case where n jobs, that is n greater than 2, go through different machines or work centers in the same order. Each work center only works on one job at a time. So Johnson gave the rule. He said that find the smallest processing time on machine 1 and machine 2. If the smallest value is on machine 1, process that job first. If the smallest value is in the machine 2, then process that job last. If the minimum time of a job for both machine 1 and machine 2 is equal, then perform the job of machine 1 at first. If there is a tie for a minimum time among jobs in machine 1, then select the job corresponding to the minimum of machine 2 and process it first. Okay. If there is a tie, then of course you have to do something. So therefore you can have type minimum time among job, then select the job corresponding to the minimum of machine 2 and process it first. That means you do like that. And if there is a tie for a minimum time among jobs in machine 2, then select the job corresponding to the minimum time of machine 1 and process it last. Okay. Then calculate the total elapsed time, that is the time interval between starting the first job and completing the last job, and idle time, the time during which the machine remains idle during the elapsed time. Okay. So, this is actually like that. Now, this is I will explain this with the help of example. Suppose sequencing n jobs on 2 machines, so by Johnson's rule. So, example is that 5 different jobs are to be processed through 2 different machines. The time in hours for processing each job is shown in table. Set the sequence to minimize the total time of 6 jobs. Now, how to do that? So, job, we saw that there are 6 jobs A, B, C, D, and in machine 1 the job A takes 2 hours and it takes 5 hours, this takes 6 hours here and 3 hours in machine 2, like that we have got. So, the job with the shortest time is 2, it takes only 2 hours in this one, and it is in machine 1, hence it is processed. Okay, it is processed. Job with shortest time is 2, so therefore it is processed first. Okay. So, this will be first, this will be first. So, therefore, you put it here because this is shortest time is 2. So, therefore, it will be first. Next, the shortest time is 3, but next it takes in machine 2. So, therefore, shortest time is 3 for job B for machine 2, therefore, process it here. So, therefore, you process it at the last. Next, the shortest time in the remaining time is 4, that is job C for machine 1, then process is first. So, therefore, bring this is the shortest time. So, put it here C first. Okay. So, it is gone. Okay. Now, what will happen next? Next, it comes that basically you have got machine 5, okay, and then you have got machine 5. Okay. So, what to do that here? You have 2 things. So, you have to, but A has been already assigned. I cannot do anything to that one. So, I have to assign E here. Okay. In the remaining time, the shortest time is 7, it is here. So, therefore, it is in the machine 1. So, therefore, come from the left hand side, and this is already. So, you get A, C, D, E, B. Okay. Let us see that 2 different jobs are to be processed. Same thing I have written in this slide again. So, now so suppose we have already assigned A and B. Now, the shortest time is for job A and E. Okay. But the job A is already assigned, hence assign job E from the first in the sequence, that means E, and you get, then job D is assigned. Of course, there is no option also because that is this one. So, job D is, so you should get A, C, D, E, B. Now, the final sequencing of processing in the jobs is A, C, D, E, B. So, we say A, C, D, E, B. So, in time is 0, in machine 2 out time is 0 plus 2, 2, then this is 2, then 2 plus 4 is 6, 6 plus 7 is 13, 13 plus 10 is 23, 23 plus 6 is 29. So, machine A will be engaged, machine 1 will be engaged like that, and in machine 2 that in time will be 2 only because it can be finished only, then it will come here, but it takes 5 hours. So, 2 plus 5 7, and then after 7 only the other job can be started. So, 7 plus 2 takes C takes 7 plus 2, that means out time will be 9. Okay, that means this is machine 2. Okay. So, this is equal to, that is 7, and then finally that it will be, say suppose it comes another one comes 9 plus takes 12, C plus 7 plus 9, actually it takes 9. So, C is if C takes 9, so then it would have been 7 plus 9 and it will become 16. Okay. So, this is the type of this thing it is done. So, similarly about D and E, you have to see that when the job comes here and this, and total elapsed time suppose comes out to be 29 hours. Okay. So, this is how that, let me give one another example little bit different. Suppose a workshop has 5 jobs J1, J2, J3, J4 and J5 that need to be processed on 2 machines. So machine A is first, machine B is second. Processing time in minutes for each job on both machines are given below. So this is job J1, J2, J3, J4 and machine A, machine B. Now let us schedule it. So find the smallest processing time. So this is smallest processing time is on basically which one? This one J4. Okay. So that is 3. So therefore job 4 on machine A. So schedule it first. So put J4 and remove J4 from the list. So remaining jobs J1, J2, J3, 4. Now what is the minimum time? It is basically, I think smallest time is 4 and that is basically on machine B. Okay. So therefore it schedule it last because it is on the second machine. So J3 should be done at the last. Okay. Then remaining jobs, okay, job J1, J2, J5. So therefore this is 5, 8, 7, 9. So what is the shortest time? 5. And which is job J1 on A. So it is first machine. So schedule J1 early. So J4, J1. Okay. And then J3 is at the last. Then in the remaining jobs 8, 7, J5, 7, 6. Minimum time is 6. J5 on B, schedule J5 late, that means before J3, so you put it here. And remaining J2 automatically goes it here. So therefore your sequence becomes J4 becomes J1, J2, J5 and J3. Okay. So now we have sequenced that thing, then we can make a Gantt chart type of thing. Gantt chart means it shows the time schedule. Okay. That means which job has to be done first. That is Gantt was Henry Gantt. Give this system, suppose we give time, okay, month wise, first month, second month, or whatever, second minute, whatever time you feel, but time is here and the jobs, okay, you do this job, then you can do this job like that. This is jobs or that one. So it will give pictorial representation. But if I want to make a table for my Gantt chart, so this table can be like this. Okay. So this is job 4. So we will just say here it is like this, job 4. It is done here 0, A start is 0, A finish is 3, on machine B it is 3, machine B it is, and finished it 11 because it takes that much time. J1 starting and machine is 3, takes 5 hours, 5 minutes, so 8. Then B start is 11 and this becomes 20, then this is 8 and 16 and this is 16 and 23. Like that we have got. So we can show it pictorially also here. So we can say suppose about machine A, this is say suppose time, and we can say about machine A, this is 0 to 3. So first job J4. So it is something like on machine A. Let me make it here. Okay, machine A. This is J4, 0 to 3. So you can say 0 to 3. So you can, and then after that 3 to 8. So this is J1, 3 to 8, like that, J1. Okay, this is J4, and then like that I can show this is J2, and this is that has taken 8 time. I am not making as per scale, and this is J5, and then I can say that J3. So we can see that total 29 hours, and here if I want to make on the machine B, then machine B, that this will be B start. B start will be 3. So that means job J4 on machine, it only starting at this one. So we can see this one. So once the job is finished on machine J4, then only J4 is start, and this is like this J4, and it takes 11, and then after that we can assign. So that way we can make the pictorial representation, and we can make it complete, okay. And you see the total elapsed time here has come 37, okay. That means 37 has come, but we see that total elapsed time is basically 37, although this one is if you see that how much time it would have taken, okay, that is 5, 9, and this is what. So we can see that maybe that some period some machine will not be utilized also. So that is what that here we can say, that you can say says if you want to show the situation on machine A, this is 29 time. So maybe that here it is a 3 hour, this is 3, this is 8, finish time I am showing 3, then 8, then here 16, then 23, 29, okay. That means this is basically the length is 6, okay. So you can say, and we can say, okay, here I can say J4, then I can say J1, then here J2, then here this is J5, and this is actually J3, okay. On the machine here it is taking 37. So why it is taking 37? Because it is of course starting from here and then we are going to up to 37, okay, much ahead up to this time. And here suppose we take that J1, so 3 and J1 is say J4, it is basically B start is 3 but B finish is 11. So that means this is actually will be like this. So up to this J4 is there. So J1 can come after that only, okay. So J1 can come here and then it will be J1, but J1 will be finished at 20, something like 20 time, okay, something like this is J1. And meantime see this, you see that J2 is already finished here at 16, but this fellow has to wait. You see here it is finished at 3 and start at 3, so 3, 3, but here 8 and this job was finished at 8, but then it has to wait, okay, okay. So this should have been that here 8 and it will start at 11, so that means that much gap is there, okay. So J4 is here, J1 is here, so this gap also pictorially we can show, is it not? Similarly suppose J2 is J1, J2 is finished at 16 but start time can be 20. So therefore J2 is finished here, so that much is waiting time for J2, but J2 can start from here, okay, J2 can start from here. So this much, so this is the finish time, this is this one. So this much gap is there for J2 and that is what this one. So we see total elapsed time, that is also called make span, is equal to time when last job finishes on machine B and therefore 37 minutes it has come. So our motive can be to reduce the make span time, okay. So for that purpose we can do optimization. Now these can be very advanced methods also, or it can be done using software. So we will not go in too much detail about that. Other than Johnson's method, I am not going to tell, that we have already told, but there are various ways to minimize the make span. So let us conclude this topic here itself. Thank you very much. Okay.